op-amp has two terminals, one's negative and the other's positive, where the output goes back with a feedback resistor, and we usually have a pull-down resistor.
Yeah, Professor, I'm still struggling with this. I've been struggling with this since year one. With your explanation, I still don't get the op-amps, and I don't know if there are any notes that will be able to help me.
Hey Felix, it seems like you're struggling with your 2130 electronics design module, right? So I have a perfect solution for you. I have the ELEC 2130 companion tool. And it's going to change your life, and it's going to save your grades, save your student career.
Indeed, it has to save my grades. My grades are not looking great at the moment. Indeed. Yeah, thank you.
All right.
Hello everyone, and thank you for joining us today. We're excited to introduce our project, a companion tool for ELEC 2130, Electronic Circuit Design. This tool is designed to simplify the complexities of analog circuit design, analysis and learning, providing users with a comprehensive electronics experience. Through this project, we've bridged the gap between theoretical learning and a real-world application, offering an engaging platform for students. Here, they can dive into the world of operational amplifiers and signal conditioning, explore advanced filter design techniques, test and expand their knowledge through an interactive quiz, and ultimately bring it all together with an integrated schematic generator. To kick things off, Hamza will guide us through the fascinating realm of op-amps and signal conditioning, which forms a foundational layer of our system. Hamza, the floor is yours.
Thank you, William, for your great introduction. As William mentioned, I will now take you through the op-amp and signal conditioning portion of our project. Our menu-driven application is designed to simplify circuit analysis. One of the key features focuses on the op-amp calculation, particularly for inverting and non-inverting amplifiers configuration. For example, user can quickly compute parameters like gain, feedback ratios by entering basic values such as resistance and the desired gain. So let's dive into a quick demonstration of how the students can use this application to perform op-amp calculations and save the results for further analysis. So as you can see here, here's the main menu. From the main menu, I'll select the inverting option to calculate the important parameters for inverting amplifier circuit. First, I will calculate the feedback ratio by entering the input resistance Rn and Rf. But for demonstration purpose, I will put invalid values at the beginning, just to show how the menu, the system is also validate inputs to prevent error from invalid values. This case, we make sure the student will have always the correct values when they are calculating amplifiers or working with amplifier. As you can see here, we have the result for the feedback ratio. Next, I will calculate the gain after providing Rn and Rf value again. The program will calculate the gain in both numerical values and in decibel, which will provide like the conversion for the students, giving students a clear understanding of the result. Once calculation is complete, I will return to the main menu and save the file. To save the file in the CSV file, we have the option back in the main menu just to make sure that they have completed all the calculation they need, so they have to go back and save everything. This feature enables students to perform further analysis and plot the graphs for deeper insights in the circuit behavior. And as you can see here, we have the results shown, all the inputs we did previously and the results here, so the student can see which exact calculation they have done, all the inputs and outputs. They can take this value and later on they can plot the graphs as needed. And that's how simple it is to use this tool to perform calculation, organize result, and enhance your result for learning experience. With that, I will now pass the spotlight to Felix, where he can explain more about active filters. Over to you, Felix.
Thank you, Hamza, for the detailed explanation on op-amp and signal condition. Hi, everyone. I'm Felix Shaw Samuel. I'm thrilled to guide you through active filter segment of our project. This part is tailored specifically for electrical engineering students to studying ELEC 2130, providing them a tool to analyze and calculate key parameters in active filters, which are pivotal in signal processing and many electronic applications. So here I have active filters. Active filters are just not theoretical, they are highly practical. So through this model, I wanted to give engineering students a tool to calculate and understand key parameters like cutoff frequency, attenuation, building a stronger understanding in signal processing. So as you can see on my left, I have the high pass filter. It allows high frequency signals to pass while attenuating at a low frequency signal. So the cutoff CB and resistor R1 determine the cutoff frequency. So as you can see on my right too, I have the low pass filter. It allows low frequency signals to pass while attenuating at a high frequency signal. And the capacitor C1 and R2 set the cutoff frequency. Now let's head to the demonstration of the code. Here's a demonstration of my code. So active filters is a crucial role in electronics, especially in manipulating signals for applications such as audio engineering and communication system. This tool allows students to explore concepts like Butterworth, Chebyshev, while also calculating key parameters such as cutoff frequency for both low pass and high pass filter, attenuation based on different pole frequencies, which are essential for filter design. So let's look at an example here. So let's calculate for maybe I'll select option 2. Let's go for Chebyshev and go for the low pass here, 100 ohms, 200 ohms for second, and 10 for and 1 for. Yeah, you can see that it has been logged as a CSV file. Someone will say, why did I use a CSV file? So I use it for easy analyzing and track over time. You can also see here that I have a filter table. So I use this feature because it complements the design tool by offering critical data for circuit simulations. So yeah, this project reflects a team effort where each member focused on enhancing different aspects. My role was basically ensuring technical accuracy and design the active filters model, while my other teammates worked on features such as op-amp designs and circuit systematics. Thanks to their contribution in this program is both comprehensive and user-friendly. So as I come to a conclusion, I would say that the active filters models bridges theory and practical applications, giving engineering students a valuable tool for their academic and professional growth. I'll hand over to William, who will walk us through the quiz menu, an interactive feature designed to test and reinforce your knowledge. Thank you.
Thank you, Felix, for outlining the numerous capabilities of active filters, and I'm drooling over my seat, thinking about implementing these advanced filter design techniques into my own circuits. Experience, I developed a quiz feature that allows users to test their knowledge in an engaging and an interactive way. Instead of introducing yet another technical calculator, my goal was to create a fun and rewarding activity that promotes active learning. So let's walk through it. Here we have the quiz. It asks the user to enter their name. We are sent it to an easy quiz, and if the user gets everything correct, then they're passed on to the next stage. And this is also fed into the quiz results. Same thing for the medium quiz. And then finally for the hard quiz. And then when all the scores have been tallied up, the user is given feedback on their score. Brilliant. Thank you. On the technical side, I designed a circuit design tool that enables users to visualize and interact with the circuits studied in the module, and bridge the gap between ELEC 2130 course content and industry relevant SPICE software such as LT SPICE, providing a practical and seamless transition for students preparing for professional applications. So let me run through how it works. Initially you're presented with a choice of 3 circuits that you could modify: an RC low pass filter, an RLC resonant circuit, and a full wave rectifier. Once you've chosen one of your circuits, say the RC low pass filter, you can then modify the circuit to however you want, and when you're done, then it's exported and saved as a .asc schematic file which you can immediately load up into LT SPICE.
Hey Felix, how did the companion tool help you?
Oh, it has helped me greatly, and I truly appreciate it. By the help of William and my professor, I've been the valedictorian of my year group year 2, and my grades have improved. So like I can say that OPSAM is something that I would look to do in the future in the career aspect. I'm looking forward to working with active filters, and you see, as I implemented code with my teammates William and Hamza, it has also benefited me because the quiz and the systematic circuit helped me in so many ways. So it has reinforced my knowledge on certain topics, and I'm truly grateful for this experience.
Fantastic. I'm so glad that we've been able to support you with this amazing software.
And yeah, and if you need any help, don't forget to shout me. I'm here to help you and assist you as a friend.